In this video, I'm going to do a demo on how to do regression using Scikit-learn, which is a machine learning library in Python. So regression involves having a dependent variable that is continuous. Now, there is a term called target variable in machine learning, and that's the same thing as a dependent variable in a regression model. We're going to be focusing on a target variable, a dependent variable that is continuous. We're not going to be utilizing classification, but just note that if your dependent variable is categorical, then you would use a different type of technique, and you would use this would be considered a classification problem rather than a regression problem. Right? So that means the data that we're going to be working with is going to be numerical. It's going to be probably involve some decimal points, and we'll take a look at that in a little bit. Right? So categorical is a little bit different. It could be numerical, but it's a discrete. It could be 0 or 1, or categorical could be things such as a binary variable, such as smoker, no smoker, male, female, etc. All right, so we're going to first start off developing a model using just one independent variable and one target variable. Now, we know that the target variable is considered to be a dependent variable. The independent variable in machine learning is, the name for that is features. So you'll hear the term features, which would be the independent variable, and then target would be the dependent variable. We're going to start off with a simple linear regression, and I'm going to show you what the data looks like. I just want to show you first all the different import statements that I have here in this cell. We're familiar with these three already. These three are the new ones related to scikit-learn, and we're not going to just yet make use of this particular object in scikit-learn, but we will be making use of this right now. And then later on, I will demonstrate what this is all about. So in this first statement, we are importing something called train test split. And that involves, this is an algorithm that will split the data into two different sets, a train set and a test set. So I'll explain a little bit more about that later on. And then we have the linear regression. So this is basically a function that we're going to be making use of that's coming out of the scikit-learn library. And then we have another type of object, which is cross-val score, that has to deal with cross-validation, where you can get a more generalized model, more reliable model, and we'll talk about that last. Okay. Now, examining the data that we're going to be working with, and this is advertising data. I'm going to run this cell so you can take a look at this. Well, first I should go ahead and run these import statements. So I get these libraries down. And then here we have the data frame. Now the data frame is going to involve 4 different data columns. And we are focusing on one target variable, which is cells. This is going to be, again, the dependent variable. And then the features are going to be either TV, radio, newspaper, or all of them. And we're going to start off with, again, a simple linear regression. So that means we're going to have one target variable, one target variable, and then one feature. Okay. If you observe the data points are in fact continuous. The target variable values are continuous. These are numerical, containing some also data points. So this involves regression. Okay. Now, before I continue, let me just show you this link. The content that I'm using is coming from this website with a little bit of additional content coming from me. So feel free to go to this website and read through what's going on. I'm also going to provide this link for your review. All right, now we have the advertising data in the data frame. And just to make sense of this data, we are dealing with 200 rows. So that means we're dealing, in the context of this data, we're dealing with 200 different markets. And the assumption here is there is a company that is spending on different type of media streams. So you have television advertising, you have radio advertising, you have newspaper advertising, and these are to somehow predict the number of sales units. We don't know exactly what kind of product, but let's just go ahead and make sure that we understand that sales and the values that you see here just represent the units of some sort of product. And now, if we pay attention to the first record, then what we're looking at is if a company spends, and since this right here, it says 230.1, it's important for us to understand that we're talking about in thousands. So if a company spends $230,000 on television advertising, then that would mean it could possibly result to 22.1, which would, in this case, we would interpret this as 22,100 units. Okay. Same thing for radio. Let's say that this is about $37,800 in advertising through radio, right? And this would be $69,200 advertising in newspaper. Now, the model that we're working with is one of these could possibly predict what's going on here. And the company managed to collect this data over time and see exactly what happened during a certain period where they spent this much on television, this much on radio, this much on newspaper, and then somehow resulted in this number of units being sold. Right now, we're dealing with 200 records here. All right, now what we're going to look at here is we are going to first inspect the data frame, right? And the thing that I'm verbally talking about is also outlined here in text. And I'm going to jump through this code cell right here and start inspecting the data frame and understanding it. We know that we already have a view of the data frame right here where we have the first 5 records and the last 5 records. But I'm going to use a method called info to give me some metadata about this data frame. We're dealing with these columns: TV, radio, newspaper, sales. We're dealing with 200 observations. Nothing is blank. I'm going to say non-null. Nothing's blank here. And then the data types for each of the data columns are floats. So that's pretty straightforward. Now, part of understanding the data is also visualizing it. And let's go ahead and see an example of how we could visualize this data. There are different functions and methods that could be used, different visualizations that could be used. And what I'll just do here is I'm going to demonstrate something called a pairplot that's coming from Seaborn. So if I write sns.pairplot, and this function contains a bunch of different arguments that we could include, but what I'm going to make use of is the x bars and y bars. And then I'm also have to indicate the data frame that we're using and things like that. Now, if I write df, that could be a positional argument. You can leave that in just like that. But then I'm going to call vvars and open up a list. And then here, what I'll do is I'm going to include the different type of data columns that I want to have in my visualization. So I have TV, radio, and then I got newspaper. Right. So that takes care of that argument. Then I'm going to call on yvars. And here, what I'll do is select cells. That means that the x axis is going to represent TV, radio, newspaper, and then the y-axis is going to be sales. But basically what this is going to do is it's going to project 3 different charts. And let's go ahead and take a look and see how that shows up. And here are these scatter plots. Right? So what this pair plot is doing is it's projecting these 3 scatter plots for each of the features. So if we're going to say TV is a feature and sales is a target, and you can see exactly how things are looking in terms of the pattern, right? Same thing for radio. So we have radio in the second scatter plot shown right here. And then we also have the y-axis being sales in newspaper. And we can tell that TV has a pretty good pattern going upwards. So there seems to be some sort of linear relationship, or at least a stronger linear relationship than the other variables that we see here, these other features that we see here. Now, I'm going to do another pair plot. I'll just go ahead and do that right here, but I'm not going to put any sort of additional arguments other than just the data frame itself. So pair plots, df, and I'm going to go ahead and just run that, right? It's going to go ahead and generate a pair grid, right? And this right here is giving us how each one of the variables, each one of the data columns pair up with another data column. Right? Now, whereas here I was being specific in terms of what I want to see in the x-axis and what I want to see in the y-axis. If I'm not specific and just put df, then it's going to go ahead and look at all of the data columns that contain numerical data and pair those up in different combinations, right? Now you can see the diagonal, or these are histograms, and these are univariate analysis paying attention to the distribution of that particular data column. So if we look at the top left, this represents the histogram for TV data. And then the next one is a histogram for radio data. But then the scatter plots are the pairs, right? So if we look at the first row here, the first scatter plot is looking at TV data along with radio. It's showing what kind of plot is going on here when you combine the two. And then we see this one right here on the very far top right, where we got that pattern going on that we saw earlier. So we know that this is probably TV in cells. So if we go down, we know, yep, that is in fact the TV in cells. There seems to be a good pattern going on here when it comes down to an increase of spending for television is going to increase sales units. That's what we're seeing here. Pretty strong pattern. Other ones are scattered, but we can still possibly make use of this in our model. But let's just go ahead right now and just continue on. So this is a very good, quick visual to get you understanding the data and see what kind of patterns are going on through each one of the data columns in a data frame. Now, if I use df.corr, this is going to provide me with a correlation matrix. And essentially what this is a numerical version of what we're seeing here up top with these pair grids. But we're looking at them from a numerical standpoint, other than the diagonal values, which are just ones all across, right? Just because when you compare TV with TV, it's going to have a correlation coefficient of 1, but you can just ignore those and then start kind of combining, see exactly what other type of correlation values that you have. So for example, television to radio, right? Now we're saying that there's a correlation of 0.054, which is a pretty weak correlation. And we know that if we observe the plots, right? If we observe the plot for TV and radio, which is this one right here, it's not really showing us a very clear pattern in any sort of direction, hence the weak correlation value that we see here. The same thing with newspaper and TV, right? So it's a weak correlation, but then TV with sales, we get a 0.90, right? So we know that in correlation, correlation is everything from either +1 to -1 or -1 to +1, anything in between. The closer the value is to 1 and it's absolute, then the stronger the relationship. Here we happen to have a 0.90 and it's positive, it's close to 1. So we know that's a strong relationship, right? And if you were to compare this right here, we know this is 0.05, close to 0, pretty weak relationship here. Now, if this were a -0.90, that would still be a strong correlation, but in the opposite direction would be a negative correlation. This is a positive correlation, meaning that as one variable increases in its value, the other variable also increases. So the more TV advertising expense, the more the sales units. So we can say that based off of this correlation, that there is some sort of association there, right? And that's pretty much what I want to cover in relation to the correlation matrix. So we can kind of get an idea of which variables are associated strongly, correlated strongly with other variables. Now, what I'm going to be doing is I'm going to focus on sales as being the target, and I want to know how these features how they'll help predict sales, right? Now, since I'm doing a simple linear regression, I'm just going to focus my attention on TV for now being the feature that's going to predict this target. So going into number 4 is conceptual stuff related to what we're doing. Some questions that could be asked related to this data. Is there a relationship between ads and sales? Well, we're gonna find out. We're gonna focus on television ads and sales. How strong is the relationship? We were able to do that through a correlation matrix. And we want to know which ad types contribute to sales. So we do have television, we have newspaper, we have radio data. We can see how each one of these measure out, and so on. All right, now we're going to deal with a simple linear regression, meaning that we're dealing with one target and one feature, right? The target is going to be y, right, that dependent variable. The feature is going to be x, the independent variable, and then we're going to have the y-intercept, which is beta sub 0, even though these are not shown as sub, beta sub 0. And we have beta sub 1, which is related to the feature. And then together, when you put them in, these coefficients together, that's what is a model. So we're creating this model that's going to help us predict cells, assuming that the model is okay. And we're going to figure out and see if the model that we're coming up with is safe enough for us to say, okay, we can predict cells. Okay, so let's go ahead and move on to this first part where it says estimating learning model coefficients. And we're going to be making use of Scikit-learn, some of the tools in this library. And then we'll kind of look at some of the methods and some of the values and just get an understanding of what's going on right now. So in this approach, what I'm going to be doing is really not involved in machine learning just yet, up until the next part where I'm going to talk about how to train the model and then test it out. So there's a little bit of a process involved. We're going to start off with this part right here, where we're going to put the data into the respective variables. Now we said X is going to represent the feature, Y is going to represent the target. So let's go ahead and start doing that. All right. What I'll do is create a variable called X, and this is going to be a capital X. I'm going to just keep with the best practice approach. So typically in Python, when you have variables, you don't capitalize variables, but in this situation, dealing with Scikit-learn and doing analytics, capital X is something that is commonly practiced that represents the feature or features, depending on the model that you're trying to do. Now, I am going to use the data frame, and I need to go ahead and make this into a data frame where it contains a column. And this is important, and I'm going to explain this more in detail in a little bit. But one way I can do this, and there are different approaches to this, but one way that you can do this is by simply opening up two square brackets and putting in the feature that you want to use in your model. So I'm going to use television. And then from there, I'm just going to go ahead and run it. And you can see that it executed. I'm going to open up a blank cell, and I want to look at the X variable that I just created, right? And you can take a look at a sample of this right here. So it grabbed the television data. Now, if you pay attention to this part right here, it's saying that we have 200 rows, so 200 records, and then 1 columns, right? So basically just 1 column related to television data. Now, this right here is acceptable, is an acceptable format in Scikit-learn if I didn't use double brackets. So for example, if I just used 1 bracket, I would still be able to run this without a problem, but let's take a look at a sample of this. Now it's different, right? Now it's showing us a series of data. It doesn't give us the information in terms of how many records and how many columns, but what I can do is say shape, and this is an attribute, and it gives me the shape of that data. This tuple is letting me know that I have 200 rows, 200 observations, 200 records, and there's a comma with nothing in it, meaning that there is no column, right? And that's because it's a series. Now, if I want this model to work, I need to make sure that I follow the instructions in the Scikit-learn documentation, and it says that in order for us to create a feature variable, an X variable, that X variable has to contain a column. Even if it's just 1 column, that means I would want to use, I can use, again, this approach, the double bracket approach, right? And now I ran it. When I do X shape, you can see that says 200, 1. So I know the fact that my data is in a column, it will work without a problem, right? I do demonstrate how to do this using the reshape approach, and you can use that, or you could use this technique, and that will suffice. For example, let me just go ahead and see if I can demonstrate this quickly. If I have TV, right? Now this is a single bracket, that means it's a series. So it's not really, there's no column involved. It's just a one-dimensional array of data. If I do .values, .reshape, and then do -1, 1, right? This is another approach where, and let me go ahead and run this cell. You can see now it's also saying 200, 1, because I'm using the reshape method, putting -1, 1, meaning that this is kind of a standard way of saying -1 is keep the same number of rows, but include one column, right? So this is the same thing as doing something like this, right? Both of these will create one column. Now I'm going to go ahead and just comment out this one. I'll keep this one. I'll probably have to revisit this later on, and I'll explain why later. But let me just run that, run the shape, and just make sure it's showing there. Good to go. All right. Now I managed to get my feature, right, which is going to be television advertising expenses. But I also need to get my target. So the target, I'm going to go ahead and say here, it's going to be sales, but I want to make sure that I spell this out. All right, so it's case sensitive. I want to make sure it's exactly written the way it is in the data frame. Now, this is going to be acceptable where I don't have to put double brackets. I don't have to use this. The target variable could be in any shape. So it could be a one-dimensional array of data, or it can just be it can contain just one column of data. So this is going to be just fine. It's the target that is necessary to have a column, at least one column of data inside of it. All right, now I can go ahead and close off with that. And now let's go ahead, and I'm not quite done. I'm trying to jump ahead here. I need to go ahead and pay attention to this part. So I split up the data into these respective variables. And now I need to instantiate and fit. So instantiate in the sense that I need to instantiate the model that I'm trying to create. And that's going to require me to use the linear regression object up top that I showed you earlier. So we're going to be making use of this right here. This is a function that I'm going to make use of. I've already ran this, so I don't have to run it again. But let me go ahead and go down right here. And to instantiate a model, I'm going to go ahead and create a variable. I'm going to call this variable LM for linear model. And I'm going to hit the equal sign. And then here's the function name. And I'm going to make sure I put some parentheses right there at the end. So this is what we mean by instantiate the model. This is a function that contains a lot of predefined code that we don't have to worry about, but it's basically the algorithm for a regression model. And we're not going to have to go through the details of all of that. And I just know that once I have this set up, then the linear regression function is going to return some information, and it's going to be placed in the LM variable. And now I'm going to refer to my LM variable, and this LM variable is going to be capable of holding different methods. And one of the methods is called fit. I'm going to use the fit and put in the data that I want to use for my model. So I have the X data, and I'm going to hit comma, and then I have the Y data. So I have my feature, which is the TV data, and then have my target, which is the sales data, right? So that is the fit approach. You're always going to fit with the train data. I haven't yet talked about that, but we will cover that in the next part. There's really no train and test data right now. Right now, we're just putting all the data that's in the data frame and fitting it and seeing how things fare. Now, we've instantiated the model, and we've now created the model using the data available, and we can go ahead and print out the coefficients related to that. Now, one of those things is there's a coefficient, there's an attribute, I should say, called coef underscore, and that's going to give me the coefficient of the coefficient value of the feature, right? Now, there's another one, lm.intercept, and that is intercept underscore, I believe. There. That's going to print out. Now, I want to be clear on what's what. So I'm just going to write coefficient. And then right here, I'm going to say intercept. And that should do it. All right, so let me go ahead and run everything. I finally ran this code, and the model was instantiated, and then I used the fit method and put the data inside. It went ahead and created the model, and then based off of that model, it printed out what the coefficient is for the feature, and then what the y-intercept is. and this is the data. Right now, you can disregard like the format of how it returns the data, but we know that this is the coefficient value for, so this is the coefficient value related to the television variable, right? That feature. And then this is the y-intercept that we would include as part of the model. Now, the way that we would work on, assuming that this is a model that is sufficient, and we'll look at how we know this in a little bit, we have enough information to use if we were to have another value, maybe in a different time period that the company is going to use, of how much television expense, television advertising expense are going to have, and what it could possibly result to in terms of sales units, right? And we can go ahead and do that using this type of approach that we see right here. Here it says, let's say that there was a new market where the television advertising spending was 50,000. Okay, what would we predict for the sales in that market? You can see exactly what's going on right here. So based off of our predictions, we know what beta 0 is, which is the y-intercept that we came up with. And we also have beta 1, which happens to be the coefficient for the television. X is going to be whatever we want to test it with. We're going to test it with 50,000. Since our data is in the scale where it's shortened out, we're going to make sure that we put the proper type of value. It's within the scale of the data, right? Now I can simply just copy this example. Let's see here. We know that I'm going to copy this right here. And I'm going to just do this manually, where I have the intercept is this value. And I'm going to add that to the coefficients, right? And I want to multiply that times X. So X in this case is going to be 50,000, but I'm going to put 50 rather than 50,000 because of how the data frame data is presented, right? So I'm going to stick with that scale and just put 50. So I'll go ahead and delete this now and run it. I end up getting 9.748, right? So this is the result. This is how many units, sales units, that were predicted based off of the model that we created, right? So it's based off of $50,000 in TV advertising expenses. Another way you can write this is using the different attributes. Now remember, there is the lm.coef, right? Underscore, and then we also have the that's a coefficient, but we also have LM intercepts underscore, right? And now if I wanted to use this, let's see here. I'm going to say that it is positive. So I'm going to say plus, and then right here times 50,000, right? I'm going to run that. Oh, I do get an error right here. And that's because it says LM, oops, it should have been LM dot intercept. There you go. And here's the results. The next one is this cell right here. It's going to generate the same thing, but a different way, where we're going to be making use of the predict method. It's already written out for us. If you're going to be using the predict method, let's say, for example, we have another a new piece of data where we know exactly how much was spent for a given month. We can enter that value and it will predict. So if I run this, I end up getting this result, right? Which is the same thing that I was able to get in these previous two examples. So the predict method is useful, but now just be careful because the predict method has to include double brackets and then the value in order for it to work. If you don't, you just have one, right, you get a value error. So it has to accept it in a way where it's a column of data, and that's why we're putting this double bracket right here. Now you notice that I do have a warning, and it's saying that X does not have valid feature names. And that has to deal with how I split the data originally. And for example, I'm going to open up a cell above this and show you the, particularly I want to show you the X variable that was split. So the X variable that was split, if you recall, it's a one column of data. So this is a data frame, one column of data. Now, because I used the double bracket, it went ahead and included the name of the feature, which is television. And that is kind of throwing off a warning when I'm trying to do some predictions off of maybe a different type of value for television expense. To get that taken care of, what I can do is when I split the data, so let me just delete this. I'm going to go back up, particularly this part right here. Right? I have these double brackets, but if I write dot values, then it will instead create an array of values and not include the feature name. So that means I'm not going to have that warning anymore, right? So let me, before I hit run to this cell, let me open up another cell, write X, you can see how that looks like, right? But now I'm going to go back to the cell. I didn't change this dot values attribute. I'm going to run it. And now same type of results. We're going to go ahead and move into the cell, run it. And now it's an array rather than a data frame, but it's an array that contains a column. You can see how we have this double bracket notation right here. So if I include the dot values, it's going to make this error go away. Now, when I run this, it is removed, right? So that's how you could clean out that warning. It's not really an error, it's just it's a warning, right? An error would not really return anything and let you kind of proceed. All right, now we can play around with numbers. Let's say the company ended up spending, let's say $75,000, right? So then I can put 75 right here, and this is how much it would generate in terms of sales units. It would generate 1,100 units, or 11,103, right? That's, I think, the better way to interpret that, right? So let's just go ahead and put 50, and there we have it. Now, when it comes down to plotting the results, we could plot this using different libraries and functions. Let me just go ahead and just do a quick df just to kind of inspect the data right here and understand what I'm working with. And I want to plot what I'm going to do is I'm going to plot this. I'm going to use sns.lmplot, and I'm going to include the x is going to be TV, and the y is going to be cells. The data is coming from the data frame variable, and I'm going to run it. Now, when I run this, it's going to show me the data that I split, right? Now, if you recall, I split them into X and Y, right? And I'm just going to go ahead and just use its original names, the original data columns from the data frame. But you can see right here that it went ahead and plotted all of the data, but it also provided me with the regression line. All right, now moving on to this next part, if we wanted to know how well the data, how well our model is, then we have to look at the R squared of the regression model. And one way we can do that is using the score method. Now, remember, when it comes down to R squared, usually what we are thinking about is a value from 0 to 1. The closer the value is to 1, then the better the model, the stronger the model. The closer it is to 0, then the less, the weaker the model happens to be. Now, to figure out the model, now, when we're saying model, we're talking about this simple linear regression model that was just created. We said there's only one feature, which is the television expenses, that's predicting sales units. That's what we're saying here. And then we kind of tested it out with like $50,000 TV advertising expenses and saw how it kind of predicted the sales units. But that we really wouldn't want to do any sort of predictions until we know exactly how well the model is doing, and that's through the R squared, right? The R squared is a proportion of the variance explained, right? And we're talking about how well the feature, right, the independent variable, the television expenses, how well it does in explaining the dependent variable, right? Now, the method for this would be score. So you would want to use the LM that was instantiated, and this LM contains the model that was created with the data. So I'm going to refer to that and then say dot score, and then enter two arguments. The feature would be the first one, then hit comma, followed by the target. When we run this, we get this score. Okay, so this is pretty close to 1. It's a pretty strong model, right? So we're pretty much saying that 81% of the variance is being explained by the feature, which is the television advertising expenses. So that it's able to explain 81% of the variance of the dependent variable, right? Which is sales units. All right. Now, looks like it's a pretty strong model. Could we improve it? Possibly. We'll take a look at another example later on. We can maybe include an additional feature. So instead of just television, maybe what if we were to also include like radio along with TV, and how well would it, how would the model be in terms of that? Would it be stronger? And if it is stronger, then maybe I can use that to predict rather than just television, right? All right, now moving into just kind of understanding what ended up happening in the back end, right? Now, remember, we split the data into X and Y. Here's how X looks like. You see that this is an array of data. And remember, it's because now I changed it from a data frame to an array. And then we can see how Y looks like. Let me go ahead and do that. I'm going to just type in Y. That's cells, right? This is a series of data. And now, if we wanted to view the like the predicted values, meaning that we know we do have a model that can predict sales. So anytime we put in a value for television advertising expenses, right, it's going to go ahead and return a value in terms of sales units, predicted sales units, right? And what I want to do here is I'm going to call the LM model that was generated, and I'm going to use the predict method, and I'm going to put the value X. Now remember, X is an array that looks like this with in a column format. If I were to run this, it will go ahead and place each of the values in X into the model, and it's going to return a predicted value of sales units, right? So that means if we look at the very first value in X, right, this is the very first value of TV advertising expenses, and this is the returned value right here, 19.73, is the predicted value if we were to have spent $230,000 in TV expenses. So essentially what I just did right here by placing the X, it went ahead and looked at each of the values inside the X variable and in that particular order, and then started predicting what those values happen to be. Right? Now, to kind of get a full picture of this in a data frame, what I'm going to do here is I have the original data frame shown right here, but now I'm going to create a variable called predicted cells, right? And so this is going to be another data column in that data frame. And this code that I used right here, I'm going to copy that, and I'm going to put it next to the assignment operator. Then I also just want to show the data frame, so I'll just write df and run that out, right? That means this new column right here is the predicted sales units when the television advertising expenses was entered into that prediction model, right? It generated that. Radio and newspaper is not something that we're paying attention to, right? So you can just ignore newspaper, radio and newspaper data columns. We're really paying attention to this feature, television, the actual sales, and then the predicted sales. And if you go through the actual sales, each record, right? Actual sales, predicted sales, actual sales, predicted sales, and so on, you'll see that they don't vary too much. And that's because we had a strong correlation between TV and sales. And we have a pretty strong model based off of the R squared. Now, if our R squared was not 80%, let's say maybe it was 20%, then you'll probably compare the actual sales and predicted sales, and they would vary pretty far, right? So that's what's going on. We created this model with one feature, one target, and then we went ahead and just predicted. We just tested out by putting all of the actual television expenses in the model and see what it predicted, and we can compare that to the actual sales amount. So here, this is the target value that actually occurred, and then here is the predicted value from the model. All right, so Now I'm just going to run this data frame, see how that looks like again, just to refer to it. But I'm going to create a visualization of the prediction model. And this is going to be built using a Matplotlib. So what I'll do here is I'm going to call plt dot, let's go ahead and do a dot scatter. And I'm going to put in X and Y, right? And these represent the actual cells, right? It's not anything predicted. These are the actual cells. When I do that, here is that pattern that we've seen before. And now, in addition to that, I'm going to also include another chart, and it's going to be plt.plot. And I'm going to write X for my x-axis data point. And then for the Y, I'm going to use that lm.predict. And I'm going to put X. Right now, if you recall, I already have a variable that contains that, right? So I could probably call that instead, which is df dot, I'm going to use a dot notation here. What did I end up calling? Predicted cells. I can say predicted underscore cells, right? And let me see if this is going to go through. Yep, you can see now the line is showing right there, but I'm going to give that a different color. So let me go ahead and say color equals red. There you go. We got our model, our linear model shown right here in red, the actual data points shown in blue. Now I can include some additional information just to understand what's going on. So if we say plt.title, I'll say simple linear regression model. And then I'll do a plt.x label, say this is TV spending. What's that? We got plt.y label, and that would be sales, or I can say unit sales. And let's see, I'm going to go ahead and run that, right? Now we have an example of this model. I'm going to go ahead and do plt.show, so just to remove that data that was shown above. But this is a visualization of this model that we created. So we see the observed value and then the prediction line as well. All right, so that is the first approach. It doesn't really involve splitting data into different train and test sets. We just made use of all of the data that is available to us. But in the next part, I am going to demonstrate the process of splitting the data first into two different sets, a train and a test set. And then based off of that, train the model using the train set. And then once the model is created, I can let that model, I'll feed that model new data coming from the test set and see how well that model is doing. And that would be the better approach, because here, using all of the data, we don't know how it's going to really, how this model is going to do unless we end up collecting another set of data and then feeding it in and seeing if the model is in fact something that was reliable or not, right? So to avoid any sort of issues, training the model using a train set and then test it with another set is the better approach. And I'll explain how to go about that next.